Hello, welcome to Lab 3 for Physics 2211. I am Matthew Mazzacano. So what I'm going to be talking about today is a simulation of a star orbiting a black hole. I'm going to be talking about the physics concepts and laws I had to use within my experiment on that simulation, and the coding I used in order to calculate data from that simulation, what my results mean, and a what-if question asking about what if this one thing that changed within my simulation, what would be the result of that. Okay, so we just talked about what the simulation was. It's a star orbiting a black hole whose mass is unknown. So the first physics concept we use is Newton's second law of motion, where the net force is proportional to the rate of change of momentum. This is change of momentum over change in time. Circular motion, define the parallel and the perpendicular components of the force, and the force of gravity, we use that formula in order to find the mass of the black hole. So this is the first frame of the simulation. We said this yellow ball is representing the star, this black ball represents the black hole, and this green ring represents the path of the orbit of the star. The orange arrow here is representing the net force acting on the star by the black hole. Pink arrow is representing the perpendicular component of that net force, and the cyan arrow is representing the parallel component of that net force. Here is another frame showing how the arrows change with the change in motion of the star. Okay, so this is some of the coding that goes into the simulator. I can't talk about all of it because I won't have enough time to, so I'll go over the most important parts. So here is the mass of the star in terms of kilograms. This is the time interval. Each time interval is supposed to be worth 1 day. So this is 1 day in terms of seconds. Here's the initial and the final velocities defined by momentum is equal to mass times velocity. So use the mass of the star times the initial and final velocities in order to get that initial and final momentums. Moving on, so the rate of change of momentum is equal to the change in momentum over the change in time, and net force, using Newton's second law, the concept we talked about before, net force is equal to the rate of change of momentum. Moving on to the next more important thing, the net force, the parallel component of that is equal to the parallel component of the rate of change of momentum. Here, the perpendicular component is equal to the perpendicular component of the net force is equal to the perpendicular component of the rate of change of momentum. Here is the radius extending from the black hole to the star. The black hole is at the origin, which is at 0.000. That's why I use this vector, this code right here. And the mass of the black hole is, we calculated this by rearranging the gravitational force formula and using F net, which we calculate from the motion of the star, in order to find the mass of the black hole. This box down here is just code using the parallel and the perpendicular components to create these arrows within the simulation. So what do my results mean? So first off, this is the averaged mass of the black hole, which I calculated. So what does it mean? So I'm asked to discuss the net force and its parallel and perpendicular components, and why that's different from the rate of change of momentum and its parallel and perpendicular components. So as seen in my code, the force and its parallel and perpendicular components are not different than the rate of change and its parallel and perpendicular components. This is because of Newton's second law of motion is stated as follows: the force applied on an object is directly proportional to the rate of change of momentum. Thus we found that the rate of change of momentum is equal to the force applied on the object. Okay, what if the black hole that we had originally observed was replaced by another black hole? If the motion of the star we observed stays the same, is it possible to find that this black hole is any different than the original in terms of mass? And no, since the mass of the star is unchanged, the motion of the star is unchanged, the velocity of the star is unchanged, and the star's orbit is unchanged. Using this formula down here, all of this stays the same. So there's no way that the mass of this new black hole is any different than the original black hole. Okay, thanks for listening to me and watching.